All right, we're going to be starting with Chapter 18, Glycolysis. Which, if you break down into its basic components, glycolysis is the breaking of carbohydrates. So what I'm going to do for this chapter is I'm going to run through glycolysis phase 1 and phase 2 comprehensively with structures, energetic components, and enzymes. And then once I've gone through it all the way, going to start zooming in step by step and rationalizing the different components of glycolysis. But the first thing we're going to do is just comprehensively go through glycolysis once. So glycolysis starts with D-glucose, and D-glucose looks like this. You have your six-membered ring. Get the hydroxyls all in the correct position, and then I like to come back through and fill in with the hydrogens. And this is going to be our D-glucose. Now, remember, this is our anomeric carbon. Sorry, I'm shifting around here. It's at the 1 position here. And then we have carbons 2, 3, 4, 5, and 6. So the first step of glycolysis, starting with D-glucose, is that we get an investment. Let me see if I can redraw that really fast for you guys. Where we invest in ATP, and this is consumed dephosphorylated to ADP in the presence of magnesium coenzyme or cofactor, and this is going to be through the enzyme hexokinase, which can also have isoform glucokinase. And what happens is we are going to transfer a phosphate group onto the 6 carbon. So that looks like this. Everything's going to be the same in terms of the ring structure, or hydroxyls, for carbons 1, 2, 3, 4, all stay the same. But then on 6, CH2O, instead of a hydroxyl, we're going to have a phosphate. So we're going to have a PO3 2-. Now, for here moving forward, when you see PO3 2-, I'm going to set that equivalent to P with a circle, just to save us a little bit of time. And on the exams, when you're drawing this, you're welcome to draw it with P in a circle as well. Then we come back through and plug our hydrogens into the appropriate positions. And this is D-glucose 6-phosphate. Which makes sense because the phosphate has been put on the 6th position. This can also be abbreviated as G6P. So this is the first step. Our second step, once we have glucose 6-phosphate, is we're going to go through an isomerization reaction. And this is going to be exercised through an enzyme phosphoglucoisomerase. And what's going to happen with this is we're not going to change the number of carbons or the location of the phosphate, but we're going to go from a 6-membered ring to a 5-membered ring. It's going to look like this. And what we have now is D-fructose 6-phosphate. Which can also be abbreviated F6P. So what we've done is we've gone from a glucose ring to a fructose ring. And without getting into too much detail here, what I do want you to see is that look at the symmetry of the glucose versus the fructose ring. You'll see right away, now that we've reorganized the structure, that we have a bit of a pseudo-plane of symmetry. It's not perfect because we don't have phosphates on both sides and we don't have a hydroxyl underneath the 5-carbon. But we're starting to get closer to a symmetrical system. That's going to be important because ultimately what we're going to do is take this 6-carbon carbohydrate and break it into a pair of trioses. So let me scroll down here. Once we have the D-fructose 6-phosphate, we have to invest another equivalent of ATP in the presence. Here's that. In the presence of magnesium. And this is going to be using phosphofructokinase as an enzyme. Whereas before we had enzymes titled for actions on glucose, now we have a fructose. So this is phosphofructokinase, and just like the title says, we're going to be phosphorylating. And you may be able to guess where it's going based on that discussion of pseudosymmetry we had before. We're still going to have the fructose ring. But now we're going to be phosphorylating this first carbon. And now the first carbon and 6th carbon are phosphorylated. And this is D-fructose 1,6-bisphosphate. Which is also known as FBP, fructose bisphosphate. And now we've reached a point in this phase of glycolysis where we've established a pretty reasonable pseudoplane of symmetry. And we're going to end the first phase by dividing this 6-carbon carbohydrate, which has been modified with pair of phosphates, into a pair of trioses. So this is going to happen through an enzyme called fructose bisphosphate aldolase because, let's see if I can get rid of that. Because it goes through a reverse aldolase mechanism. So this is fructose bisphosphate aldolase. And it divides the fructose 1,6-bisphosphate into two new compounds, dihydroxyacetone phosphate and D-glyceraldehyde 3-phosphate. So the first is the dihydroxyacetone phosphate. Move this up a little bit. So we have the dihydroxyacetone phosphate, and you can see that acetone is, remember, this structure with a simple ketone, and the dihydroxyacetone has both of the carbons at the 1 and 3 position hydroxylated, and then one of them phosphorylated. Hence the name dihydroxyacetone phosphate. And the second compound is the D-glyceraldehyde 3-phosphate, or G3P, and that looks like this. And glyceraldehyde, structurally very similar to this. This is just a phosphorylated glyceraldehyde. Now, the final step in the first phase is that we move the dihydroxyacetone phosphate, dihydroxyacetone phosphate, over to glyceraldehyde 3-phosphate using triose phosphate isomerase. And actually, this can go both directions. And what we end up with at the end of the first phase is from D-glucose, we get 2, let me see if I can change colors here, 2 equivalents of glyceraldehyde 3-phosphate. Oh, that's what I was looking for. So let me shrink this down a little bit, move it a little bit slow. But here we've started with glycolysis, and this is phase 1. And we started with the glucose, and we ended with glyceraldehyde 3-phosphate, 2 equivalents of glyceraldehyde 3-phosphate per glucosin. And also remember that we've invested 2 ATP at the hexokinase step and the phosphofructokinase step to get here, because we had to use the ATP for each phosphorylation event. Now, let me zoom in and we can start phase 2. There we go. Okay, so starting phase 2 of glycolysis, we now remember have 2 equivalents of glyceraldehyde 3-phosphate. So instead of writing 2 next to every single thing, just remember that everything that show below here happens 2 times per. So to get started, it's a little redundant, but I'm going to redraw the D-glyceraldehyde 3-phosphate. So we get our aldehyde. So we're starting with our glyceraldehyde 3-phosphate that we had below, and we're going to have our first reaction with glyceraldehyde 3-phosphate dehydrogenase. And this is going to involve reducing equivalents and inorganic phosphates. So I guess enzyme first, glyceraldehyde 3-phosphate dehydrogenase. And the inputs are 2 equivalents of inorganic phosphate and 2 equivalents of, oh, excuse me, this is per, so per is a single equivalent of inorganic phosphate and NAD plus in and out, we'll get an equivalent of NADH plus 2, oh my goodness, I'm making a mess, plus a proton. There we go. Now, we had a discussion in class previously in chapter 17 regarding reducing equivalents and how they vary between anabolic and catabolic processes. So recognize that for glycolysis, the reducing equivalent that we will see over and over and over again, and in the TCA cycle, and in electron transport, will be NAD plus and coupled with NADH. So what we're going to see is a dehydrogenase event where we go from glyceraldehyde 3-phosphate to 1,3-bisphosphoglycerate. That's going to look like this. One 3-bisphosphoglycerate or 1,3-BPG. Now, once we have 1,3-BPG, we are going to hopefully not have things continuously pop up in the middle of lecture here. Still figuring out the tablet thing. Actually bring back some of our ATP. So now we're going to do a reaction coupled to ADP going to ATP. And remember that everything we're drawing here is times 2. So even though on the phase 1 everything was single, so we invested in single ATP twice per glucose, for each one of these glucose we put in, we have 2 glyceraldehyde 3-phosphates. Therefore, we will have 2 1,3-BPGs. Therefore, for each glucose, we will be generating 2 ATP per glucose invested initially. So this will be our break-even point where we've put 2 ATP in, and now we'll be getting 2 ATP back out. And this is going to take place through, like I said, make sure I'm not crossing everything, our glyceraldehyde 3-phosphate dehydrogenase enzyme. Before, and now we are phosphoglycerate kinase. And this dephosphorylation is going to look like this. So we've gone from 1,3-bisphosphoglycerate to 3-phosphoglycerate. Now, please take note when I draw the carboxylic, or not carboxylic acid, this is in the conjugate base form, the carboxylate. This group is actually, looks like that. but just for space sake, I'm just drawing it in the shorthand, COO minus. However, if you want to draw it long form like this to the right, that's just fine. If it helps you keep track of what's going on with your phosphorylations and dephosphorylations, that would make sense. So now that we've got 3-phosphoglycerate, we're going to undergo a isomerization reaction or through a mutase enzyme. And the 3-phosphoglycerate is going to have its phosphate transferred to the 2 position. So let me scroll up a little bit, make a little bit of room here. Using phosphoglycerate mutase enzyme, we're going to be moving this phosphate to the 2-carbon. And notice I don't put any stereochemistry on the 3-carbon at this point, because with CH2, there's no point in trying to define stereochemistry because we don't have 4 unique groups around that carbon. And this is now 2-phosphoglycerate. Or 2-phosphoglycerate. And once we have 2-phosphoglycerate, we only have 2 more steps. From 2-phosphoglycerate, we're going to perform an enolase reaction using enolase enzyme. And what's going to happen is, in the presence of our cofactors, we're going to be shedding an equivalent of water, and the cofactors include potassium and magnesium. And what happens here is we're losing water by taking away the hydrogen on the 2nd carbon and the hydroxyl group on the 3rd carbon, and we're going to end up with the following compound. Where we've done a dehydration, forming a double bond between the 2 and 3 carbon, losing the hydrogen and hydroxyl group that I showed above. And this is something you've probably heard of before. This is phosphoenol pyruvate. And phosphoenol pyruvate, or PEP, undergoes one more transformation, which gets us above the break-even point. We're going to yield another ATP in this step. But remember, this is times 2. So for each glucose in initially, we're going to end up with 2 pyruvate and a net of 2 ATP per glucose in. So we have our ADP in. Let me make that look like a P. ATP out. We need our potassium and magnesium. And this is going to happen through pyruvate kinase. Just need a little bit more room. And we're going from phosphoenol pyruvate to pyruvate. And what happens with this is it undergoes a keto-enol tautomerization and dephosphorylation coupled, where the double bond moves to the 2 carbon, making a ketone, and we now have pyruvate as our final product. Now let's zoom back down. Take a look at the big picture. Maybe a little bit more. Maybe I can shrink it a little bit more. Get all in screen. Oh, close. I'll just move around a little bit. So we have our overall picture now of glycolysis. Phase 1, we're taking D-glucose and we are modifying it to get a pseudoplanar symmetry with a pair of phosphorylations which allow us to cleave it into a pair of triose molecules which are isomerized to a pair of glyceraldehyde 3-phosphates as our final step in phase 1. And then in phase 2, remember everything here is times 2, we have 2 equivalents of glyceraldehyde 3-phosphate that get subsequently phosphorylated using a reducing equivalent NADH and inorganic phosphate. We then recover our ATP that we've invested so far. We end up with 3-phosphoglycerate, which then has to move the phosphate from the 3 position to the 2 position. Once we've moved to the 2-phosphoglycerate, we can do a dehydration reaction forming phospholynyl pyruvate in the enol form, which is high energy, and it wants to go to the keto form, which is our final product, pyruvate, and this is also where we get our ATP surplus from the process. So that is the overall summary of glycolysis, phase 1 and phase 2. And now it's time to talk about reaction coupling in glycolysis, why it's important, and dive into each of these steps in more detail so we can really get into the nitty-gritty of glycolysis. So one of the questions that we discussed in first semester was, why do biochemical systems rely so heavily on coupling of reactions? And there were a couple rationale that we used. One, coupling of reactions. Oh, let me change my my stuff up here. One rationale is that you can take things that are non-spontaneous and through coupling with a favorable reaction make something spontaneous or favorable. And this opens up biological processes to a whole host of chemical pathways that would otherwise be unavailable. Now, a secondary but very important component of this is that critical steps which are inherently non-spontaneous until they're coupled will not proceed on their own. So through coupling, we get control over when something proceeds, because coupling is a concerted event. Using enzymes, right? So we have control over enzyme function. We therefore have the ability to turn coupling on, turn coupling off, or in more complex systems which are allosterically regulated, modulate the degree to which they're turned up or down using allosteric effectors from the pathway itself, which give you an indicator of energy status. So big picture here, coupling of reactions in glycolysis and other systems is important because it allows to drive non-spontaneous reactions to spontaneous reactions through coupling, and it also gives us absolute or essential control over these processes which we don't want to occur without biological input. Because otherwise, if these just happened on their own, we wouldn't have any control over them, and we wouldn't be able to benefit from them via metabolic regulation. So, now zooming in a little bit on glycolysis itself, know that in glycolysis, we are taking one equivalent of D-glucose, and through several steps, making two equivalents of pyruvate. In addition to the two equivalents of pyruvate, we are also getting two equivalents of ATP. Net for the entire system per unit glucose. Now, these are two different processes, but before I go any further, let me show you the structure of pyruvate again. Where the central carbon is oxidized to a ketone. And then let's take a look at lactate. And notice that lactate has a hydroxyl group at the central carbon versus the ketone, meaning that this central carbon, the only difference between these two compounds is the oxidation of the 2-carbon from the hydroxyl to the ketone. So I'm pointing this out because we're going to draw an analogy here, which is really important in terms of energetics. So note that the process of glycolysis converts some, but not all, of the metabolic energy of the glucose into ATP. There's still going to be quite a bit of energy left over, but we're going to be converting it into ATP. The free energy change for the conversion of glucose to two equivalents of lactate, which is the anaerobic route of energy production, is minus 183.6 kilojoules per mole. So what this looks like is we take glucose through several steps of lactic acid fermentation and contracting muscles. We go to two equivalents of lactate plus 2 protons, and we get a delta G naught prime of negative 183.6 kilojoules per mole. Notice this is very favorable. So this process occurs with no net oxidation or reduction. Although there's lots of steps in the pathway which involve oxidation and reduction, which we're not going to get into, they compensate for each other exactly, and the conversion of molecules of the glucose to the 2 molecules of lactate involve simple rearrangement of bonds, and there's no net loss or gain of electrons in the process. So this is ends up being a very favorable process where we're going without oxidation, net oxidation or reduction, to a more stable state energetically, which is highly favored at negative 183.6 kilojoules per mole. Now, the production of 2 molecules of ATP requires energy. So if you have 2 ADP plus your 2 phosphates, and this gets combined to form ATP and water, the delta G for this is going to be 2 times 30.5 kilojoules per mole, which is about 61 kilojoules per mole. See if I can make that point a little bit more definitive. Now, it's not perfectly coupled. But if you think of the chemical process of glycolysis to being very similar to lactic acid fermentation, because the starting products are identical and the end products are nearly identical, minus a single oxidation of a carbon, you can think of glycolysis as the coupling of these two reactions, where you would say that if we added them up, we could say that glucose plus 2 ADP plus 2 phosphate yields 2 lactate plus 2 ATP plus 2 protons plus 2 waters. And if we did this energetically, we would say that for the coupled process, delta G would be negative 183.6 plus 61, because that would give us negative 122.6 kilojoules per mole. So this is a highly favorable coupled process. From this, it's reasonable to justify that the coupling of the conversion of glucose to pyruvate in glycolysis more than enough justifies the production of some ATP in conjunction with it, without even consuming all of the available energy, while keeping the process overall highly spontaneous. So I think that's going to be a good place to pause this particular video, and I'm going to upload this one, and in our second lecture on this chapter, I'll do the dive into each individual reaction, starting with glucose going to glucose 6-phosphate, fructose 6-phosphate, etc., all the way through both phases. And then we'll wrap up that lecture with a little bit of discussion about the overall regulation of glycolysis. And that'll be it for the glycolysis chapter. So I'm going to wrap this one up, and I'll be seeing you in a little bit.